Okay, we're safe. Now we don't have to think about our feelings anymore. Okay, cool. So, stack. Wait, did I not update this? Oh, that's supposed to be a meme for keep at it. But okay. Today we're doing ownership. This is like chapters 3 and 4 of Rust book. Why do we go out of order? I wasn't really teaching Rust this term. I was teaching in Rust, so it makes sense that we get back to some Rust concepts later. Over the course of this term, I should report this all back to you. I've basically convinced myself that I don't like Rust, but that it was the right language to teach this class in, and I really expected at this point in the term to think the opposite way. So you are probably at some point in time in your life going to be asked to say something that is your opinion about a programming language. So I'm going to talk for 2 minutes about programming languages, and you can just agree or disagree with all of these things and then use them, or you can have your own ideas. So what I thought I would like about Rust is that it is a modern language that is supposed to have some functional programming features in it. We have never, this term, written one function that returns another function. And I wrote those in CS1. In CS151, there were problems where the correct solution was to write a function that returns another function. Specifically on Adventure, that should have happened, right? And we don't teach how to do that in CS151, but it's actually quite straightforward to do it in Python. It's relatively clean. I don't even know if you can do that in Rust, because it's never come up to do that, because there's so much blasted syntax in this language. There's just you're just always using a trait to solve things, or the type system to solve things, or some crate to solve things. So you're never writing your own high-level code, and that was shocking to me, because I heard Rust was the functional systems programming language. And it is, right? There's not classes in it, so I haven't taught you classes. Today I'm going to teach you about structs, which are not classes. But they look way more like classes than I want them to look. So anyways, I ended up learning all this stuff about Rust alongside all of you, and I kept waiting for the parts of the language that exist. There's iterators in Rust, right? We just don't use them. And we, essentially, the only time I used pattern matching is when I invented a contrived example to teach pattern matching, right? And then I have, never found another time to use it. So there's all this stuff in Rust that I sort of expected to and it just seems like you don't use it. On the flip side, I write Python all the time, and I write the worst Python you've ever seen, but I write it the way I want to write code, right? So it's other people's Python doesn't look like that, but I sort of get to use the sort of design patterns I want to use. So we're going to talk just a little bit about design patterns today. That was surprising to me. Separately, this other thing happened. You all seem to be doing really well this term, and I don't know if you feel like you're doing really well, but I'm looking at your code and it looks way better than it did when I taught this class in C. And separately, I am way better at teaching C than Rust. So that was not me. That was not a Calvin difference, right? We probably don't want to argue that, on average, you are, markedly smarter than the last group of students that took this class. That's, a weird thing to argue. Now, it could happen, right? You might all just be geniuses, right? I can't do anything about that. You could just be cooking the numbers, right? And you seem pretty smart. But, it would be weird to assume you're dramatically smarter than everyone else, right? So, since I'm worse at teaching, you should in theory be about the same as the other students. The only thing we changed is the language, and actually some of the problem sets are harder too. SHA-512 is a little bit harder than 256. I think Wordle's a little bit harder than Enigma, and definitely ECDSA is harder than RSA. It's everything should have been harder, and you're doing better. So that has to mean, and this is what it's convinced me, Rust must just be a good language. And I can't figure out if it's a good language for people that know Python, which is what many of you are, or it's just a good language in general. Because when I write it, it just feels awful. But I also haven't been writing it for that long. I started writing Rust 8 months ago, maybe a little more than that. So maybe it just hasn't set in yet. And you haven't been writing it for that long, so you'll have to let me know. But anyways, so Rust to me kind of wasn't as advertised. But the thing that really gets me about Rust is its error handling is so good. Every time there's a panic, it's because you did something you weren't supposed to, right? It's never ooh, how was I supposed to? The language was going to do that. It's no, you didn't unwrap something. What's wrong with you? Or oh, you wrote unwrap and just assumed that it would work every time. The entire reason you wrote unwrap is because you're not supposed to do that, right? So I think Rust, and perhaps the compiler as well, is just really kind of forcing you all to write really good code. And so kind of hard to complain about that. That's just super cool. So good for you all. I'm happy for you. I kind of feel bad for everyone else I've ever taught now, because I guess I should have started teaching Rust like some amount of time ago. I don't know how long. Anyways, now we're going to teach about the most Rust thing that has ever rusted, which is ownership. Ownership was another one of the things I thought I would like about Rust. I don't really feel like it was advertised. It sort of seems to me like it's just you're not allowed to use variables more than once, which is like, that's obviously you can design a programming language that does that, but that didn't seem like interesting to me. But I'm going to use ownership to motivate a bit of a sort of hardware operating systems architecture concept on the stack and the heap, which is something you should all know about. I just taught briefly in Rust book. I believe this concept is harder to understand because I taught you Rust instead of one of the other languages this term. We will see what happens. Separately, we can argue it matters less because Rust exists now. I don't know. So I'm going to teach this. I'm going to tell you the things that I think you need to know or that are interesting. I am not teaching you anything that was not in Rust book, so I'm making no claims about what you should know beyond that, so I'm not doing any extensions. I'm keeping it strictly within the realm of what the Rust people seem to think you should need to know, and I think that alone is interesting enough. Okay. Ownership is the set of rules that govern how a Rust program manages memory. I don't really agree with this way of thinking of this. Ownership is an abstraction maintained by the Rust compiler that it uses to prevent there from being memory errors, is how I would say this. This is a compiler technology. This is a compiler idea. This is something that you can tell the compiler you want to do certain things with clone, or with reference, or with mute. But fundamentally, it is maintained and enforced by the compiler. Once the code is compiled, there is no notion of ownership. The code just runs. And if it compiles, then it will run. That is the theory. Some languages, like Python, and Java, most importantly, but you know Python, have garbage collection, which is this sort of background process. It's like there's a server somewhere, but really it's just another process on your computer. Your Python code's running, you turn on Python, you start running it, blah, 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 you're doing your Python things. Every 500 milliseconds or something, that Python code is paused. Another piece of code turns on. Usually it's still written in the same language. It comes in, and it goes through all of the variables that have been used. And if it sees if someone doesn't know the name of any one of the variables. So, how do computers work? Terminal? Is that what I'm going for? Python. So, x equals hello something. X equals hello world. You know Python lists are immutable. That means no aspect of this hello something persists into this hello world. So at some point in time, the garbage collector is going to come through here, and it's going to get rid of the information at this location in the computer. Now, there's already no way to refer to that information. But if I throw enough information in variables and then overwrite those variables, eventually I'll run out of storage space unless the garbage is collected. I think there is... You can find the garbage collector, and you can even like loop over the objects the garbage collector knows about in Python. So for example, like print is known to the garbage collector because it's a defined variable, and x is known as well. So there is a garbage collector in Python. You can go and investigate it. I don't find garbage collectors academically interesting. I think the academically interesting way of doing memory management is doing it yourself. Obviously, I can write a program that reads my code and sees if any variables aren't being used, right? That doesn't seem interesting to me. How can I write programs that deal with potentially arbitrary sized objects, so I don't know how much memory they're going to need until they start running, without using garbage collection? That's what's interesting to me, right? In the other language, C, you have to talk to the operating system, and you say, "Dear operating system, please give me this many bytes," and the operating system will say yes or no. And if it says no, that's when you should panic, same as in Rust. You basically unwrap that value, right? And if it says yes, then you get to play around in those bits and bytes. But if you ask for too many bits and bytes without ever giving any bits and bytes back, eventually the operating system says, "That's stupid, you're stupid, shut up," and kills you. And it's killing a process, so it's not actually violent, right? But like, yeah, you can do that, right? In Rust, I'm assuming there's some way to ask for too much stuff, and the operating system says that's stupid, you're stupid, right? But in practice, we don't actually give the memory back to the operating system sort of intentionally or using a function. Anywhere in Rust, there is, I think, something called drop that does it. But rather, what happens is we have ownership. And when no one owns something, it is given back to the operating system. So that's how to think about it. Oftentimes, this is introduced in the concept using a move. So let's get a move going. Cargo, new. Oh, what's an in class? Weird. What's in numbers? Okay, that's a Rust thing. Okay, so we're just going to go into numbers, whatever that is. Nvim, sorc main. Oh, that was from the numbers lecture. Yeah, yes, that was from this class. Okay, okay. So what are we doing? We're gonna take this code and we're gonna throw it in Rust. Okay. So what does this do? I am going to create a string, and I am going to specifically create the data structure version of a string. This is not just a series of characters. This is some other stuff. This is the data structure or whatever, right? So I'm going to take string, and I'm going to create it from hello. This hello, that is the string slice. That is just 5 bytes, maybe 6, I don't know. So some finite number of bytes that I know when I turn my program on, right? Then from that slice, I'm going to create a data structure that contains that slice and diagnostic information. It's going to contain methods, it's going to contain length, it's going to contain so on. I'm going to call that S1. So I'm going to create a variable named S1. Okay. When I create that, the next thing I'm going to do is I'm going to create a function called takeOwnership. What is takeOwnership going to do? Well, it is going to receive that string, and it is going to print that string, and then that function is going to return. It's not going to return a value. The only thing that matters is that that function ceases to be. It reaches the end of its execution, and then it's not around anymore. When that function is not around anymore, and it goes to Valhalla to be with its honored dead, it takes that string with it, and that string no longer exists. The memory that was used by that string, which is a data structure, is returned to circulation in the operating system, and other people can use it again. What that means is this: if I uncomment this line, rustc will explode in a flurry of rage and prevent my code from compiling, right? Or perhaps it will actually be very nice and tasteful about it. Let's see if it's nice. Oh, that was actually relatively polite, right? Could not compile. Like, it tried really hard to compile, right? Okay, so that actually, I think I was viciously slandering rustc there. It's being very polite. Okay, so let's go ahead and let's comment this back out. And now, the takeOwnership function. Here, we'll look at it. The takeOwnership function takes string. String vanishes into the shadow realm right at the end, the same time takeOwnership does. And we can never use S1 ever again. And if we try to use S1, it's not allowed. So, somehow, Rust has to make sure you don't take memory forever. And the way it does that is by only letting you use variables once. And as soon as you use the variable, you can never use it again, which means it can give the memory back to the operating system. Okay. What if you really want to use something twice? Well, then we have to sort of deal with all of this stuff in the ownership model. I'm not going to say all of that because I said all of that out loud. Okay. I do want to introduce this specific term, invalid, and I'm going to get the compiler to say invalid again. Why am I doing that? Okay, cargo run. Okay. Where does it say invalid? A lot of text here. Oh, so I'm going to do this later, but I think that this is all coming from rustc. I'm getting it from cargo run. I don't think it's strictly speaking necessary for me to have to read the volume of text that Rust gives me. But again, this is defeated by my hypothesis that you all mysteriously learned how to program this term, right? And I didn't teach you, so you learned from somewhere, right? So I was a little surprised by just how much text there was here, so I started doing word count on all of the things that came out of Rust. And I just personally think I can say you used an invalid memory location in fewer than 1,307 characters. That's how I feel about it, right? But I must be wrong. I must be crazy, okay? Right? So, what do we have here? Let's read through this. Borrow of moved value, S1. Okay, so we create the string. Okay, move occurs because S1 has type string. String is a data structure. They say here it does not implement the copy trait, but really what that means, to me what that means is this thing is of arbitrary size. We don't know how big it is, so we can't just make copies of it for free. So, the value is moved. Its ownership changes from main to take ownership at line 4. Okay? Then at line 7, we attempt to use S1, but we don't own S1 anymore. So that's like going back to my apartment that I don't still have a lease on after my lease expired or something. It's like that notion. It's like it no longer belongs to me, right? Now, they give me a few different ways to deal with this, but one of the most obvious ones is I can clone it. So let's take a look at the clone. What's that going to do? Well, if I clone this, that's like if I was living in an apartment and then I secretly, on the side, built a tiny home in the mountains, right? And I'm going to keep my tiny home in the mountains even when my lease expires on my apartment, right? Oh, look at that. It's very short. Let's see what this actually does. So, when I do that, I am still able to look at both of them. Why? Because now there's not just one thing. I am creating more stuff. I'm spreading the wealth. I'm creating a bigger pie. I'm sort of like education and healthcare policy, right? It grows the GDP without taking away from anything else, right? So this is the solution to sort of the Rust problem is, I just move something else. And presumably you've been using clones all term and being variously, annoyed about them. So this still means the same amount of memory is going away. But when I add that clone, I'm now reserving twice as much memory. So that's what's going on here. We can take a look at this in a slightly different manner using something other than a string, a not data structure. So I'm going to use x, which is an I32, an integer 32. That 32 means I know exactly how big it is. And so I'm going to go ahead and grab this. This is snippet 2. Okay. We're going to create a variable x. It is an I32. I don't have to label that. It's going to be equal to 5. It can be equal to whatever you want. I'm going to copy x, or make a copy of x. There is no ownership taken of x because x is not an apartment building. X is a public sidewalk. No one can own it. It is one square on the public sidewalk. It is of a fixed size, and there's no way to sort of create a public sidewalk that's larger than that, right? So when this works, make copy will receive the numerical value, 5, but it will not take ownership of x. It will be able to print out that value, and then back in main we will still be able to print out that value because it is just the value 5. It is not a data structure that can grow and change. It is not a value that can take on potentially infinite size. This works exactly as expected, right? There's nothing really complicated about this, but it is fundamentally weird to me that some variables behave differently based on whether they can be potentially infinite in size or not. Rust describes this using the copy trait, but there's other ways to describe it. So, when make copy is called, what is happening? A bit-for-bit copy of the value 5 is created. And we can create bit-for-bit copies because we know how many bits we need. We need 32 bits. So we use the 32 bits to make a bit-for-bit copy. So when make copy is called, I take a new 32 bits. I just copy over the other ones. I do this easily. It is inexpensive. The original variable x remains valid. And also, alterations made to that x inside, for example, make copy, will not persist back to the original version. You've seen this before. X equals 7. Def add 2. we'll call it y. Y plus equals 2, print y. X, add 2, x, y. Oh, that's not what I meant to do. X is unaltered by having 2 added to it in a function. This is common namespace stuff. You've been doing this forever. And then what's the difference? What if we take x is 1, 2? I don't think I can add anything to x then because it's the wrong size, but we can make a different x. Add 2, let's see. Y plus equals 2, print y. X, add 2, x, and then this permanently alters the x. So this is the difference between a data structure and a value. That's how I think of it. Okay. We can also solve this one other way, which is with a borrow. A borrow means that you, as the sort of calling function, retain ownership over the data structure that you share with the called function. I am main. I call up my friend. I pick up the phone and I say, calculate length. And calculate length says, calculate length of what? And I said, look, I've got a string here, and I'm going to let you look at it, but you can't have it, okay? You can only look at my string. And so I give the person I'm calling the address of my string. The person drives over to the string, takes a look at it, calculates the length, and then tells me the length. So that's what this code here does. Let's run this. Nvim circ main dg. Okay. So, what are we doing? Create the same string as before. We are going to calculate the length on the string, but we are only passing a reference. We're letting someone borrow it. Or perhaps this is like, I'm giving someone the key to my apartment to check on my cats, but they don't get access to the lease or something, right? So, yes, you can take care of my cats. We do this using the ampersand, and this ampersand shows up in another place. It also impacts the type of the function. Calculate length no longer receives a string. It receives the location of the string, or the name of a string, or the email address of a string, some way to find the string. It's able to go and investigate the string, but it cannot manipulate the string. And when it is done with the string is still there, because it's only borrowing it. So as soon as this function returns, ownership of s returns to main, which means I am able to look at s, I am able to print it out, and I'm also able to print out its length. Let's go ahead and run this. Cargo run. Nothing too exciting, nothing too surprising, but that's how it works. Let's break this. We're going to get rid of the ampersands. And that is immediately against the law. Instead of using ampersands, we can use clone. What does clone do? Instead of letting someone borrow the key to my house, I create a new house. This works. Or we can just go back to using ampersands. Both of these changes get the code to work, but one of them uses extra memory. Cloning uses extra memory, and sometimes when you see errors pop up in rustc, it'll say, hey, consider cloning here if the memory cost is acceptable. It never is. Always borrow. And then this will work as well. So I think this is what I say, but in general, if you have some data that you're persisting, if you've like built a data frame or a vector or a list or a binary search tree or whatever it is that you kids make these days, you're all into hash tables, aren't you? You're such the hash table generation. When I was your age, we had to use binary search trees for everything. Now you all get to use your hash tables. But so you got your hash table or whatever, right? And it's fine. Okay, so you've got your hash table, you're keeping your hash table around, and like maybe you pass your hash table into something, you're like, hey, can you give me the first 3 alphabetical keys in this hash table? And the function's like, sure, that's fine. Do you want me to drop this hash table into a lake of eternal fire such that it's no trace of it ever exists when I'm done with it? I was like, no, why would you do that? I am only letting you borrow my hash table. And they're like, well, you didn't say that in the function signature. So rustc just created a clone, duplicated your 10 trillion terabyte hash table, and now your computer's really slow. And I was like, well, who wrote all of that code? And it was me. It was me the whole time, right? So don't do that. Just pass ownership around if you need it. I often find myself, when I'm doing things like reading files, I read a lot of files with headers and then there's updates to it. So I keep the header around forever. So I've got this data structure that's persisting that I might be making small changes to. That's always passing around references. The Rust thing, in my opinion, is this borrow idea. Ownership is retained by S, or ownership is retained over S by main. So the function that created the variable retains ownership over it, but you're still allowed to use it for something. You allow someone to borrow S and study its length or whatever. Maybe this is why Rust is winning. I was initially told this was why Rust is winning. I no longer believe that. Now I believe it's the error handling. But nevertheless, this is highly compatible with the error handling. Right? Rust has a very, very sophisticated compiler that is able to enforce these rules and also type checking rules. And in between all of those, it is very difficult to compile Rust code that does not do what you intend. In fact, I gave an example in the numbers lecture if the Rust compiler would not allow me to compile code that did do what I intended because it thought I was using unintended features of integers, right? So Rust is very aggressive about preventing you from doing things you shouldn't do. What is happening under the hood here is the difference between the heap and the stack. And so now I'm going to tell you about the stack. The stack is easy to understand once you understand it. It is recursively simple. I tried to explain it once and found out that I didn't have a great way to explain it because I cannot help myself from thinking about the stack abstract data type every single time I start teaching about the stack. And then the next thing I can't help myself from thinking about is what is actually just going on physically in transistors, which is the most confusing thing in the world, right? So instead, I copy-pasted Geeks for Geeks HTML into Google Gemini and told Gemini to reformat it into Markdown, and that's where these slides came from. So I'm passing this off as my own. The memory stack is a last-in, first-out storage device. Is that true? No, but it's close to being true, and it was true 20 years ago, so we can pretend it's true. Okay? It organizes a portion of the computer system's memory in a very, very tiny portion. Talking infinitesimally small by the scale of overall memory. A couple variables, basically. Your working variables. It is named after the stacked abstract data type, but it is not the same as the abstract data type. Specifically, modern computers can look 3 or 4 entries up and down on the stack, no problem, all the time. I'm going to introduce a term here that I think is important to introduce in this type of class. Perhaps I should have introduced it sooner, but I think this is the most useful time to introduce it. Is the term leaky abstraction. The stack is an abstract data type. What does abstract mean? It means that we don't really implement stacks in any sort of programming language. We can use a list to provide the features of a stack, which is the push, pop, and sometimes peek operations, right? But those are all just abstractions over a lot of code that has to run and sort of implement those features, and we sort of have to make decisions about it. What happens if you pop off an empty stack? I don't know. That's a design decision. That's not really described in the ADT. And it can't really be described in an ADT because in Rust that's a panic, in C that's a null pointer dereference, and in Python you probably just get none back. But you can also probably push none onto your stack, right? Fundamentally, the stack is something that exists in hardware. There's a series of transistors in your computer, and they store a sequence of bits, and there's breakpoints in the bits, probably at every 64 bits or perhaps every 32 bits. And different values can be written to those different bits at times. And the computer keeps track of the location of those bits and knows where it is in the stack relative to the beginning or the end of the stack, right? Now, in Python, you never think about those transistors at all, ever, I don't think. In Rust, you think about them all the time because every time you have to write clone or pass a reference, the reason you're doing that is because you're working with something that doesn't fit on the stack. So, I's claim, nominally the stack is abstracted from the programmer. We don't think about whether there's just a working space of a few bits and bytes that exist within the CPU, and we're allowed to work with them. You don't think about that in Python, right? Rust forces you to think about it because you have to decide whether to use references or clones. And you only have to decide to do that with certain types of variables. So I'm calling this a leaky abstraction. The abstraction of the stack leaks into the language, and it forces me, as the programmer in the higher level language, to make design decisions about how I write my code. And specifically, it's the clone versus reference design decision. I have to make that every single time I deal with something that doesn't fit on the stack. So, how does this work in hardware? Do I want to draw this on the board? Oh, no. I almost started drawing on the board with a glue stick. Do you see there's just a glue stick over there and there's no markers? They're trying to get me. I would be very sticky. Oh, I don't know. Like, I have... Let's do it. Oh, there's not a projector that goes on that screen in this classroom. Okay, I'm not sure how I want to do this. I have diagrams on the slides. We're going to see if those are okay. If you ask me questions, I'm going to draw. Okay. I'm a computer. That's not true. We're pretending I'm a computer. I'm portraying the character of a computer, right? And as a character that portrays a computer, I am good at remembering a few things. One thing I'm good at remembering is the stack pointer. The stack pointer is the address in computer memory of where the top of the stack currently is. And then I also have a few other things I remember, and I'm not going to give you a number or size of them, but I have something called data registers, and I use data registers to remember values of fixed size. In my computer, I have 64 registers of size 64 bits. You can think of it as like you can remember 4 phone numbers at a time or something, right? I have my data registers, and I have my stack pointer. Stack pointer, maybe the best way to think of that is it's the last item on your to-do list. This is something you write down and you keep track of the end of it. I'm using the term register here. Have I told you what registers are? Do you know what registers are? Okay, good. A register. Okay. In mathematics, it's very useful to have variables. We all understand this. Programming languages were derived from mathematics, so they have variables which are themselves useful. People wanted to make computers that could run programming languages. Variables don't exist in real life. They're not like a real thing. So what do? They say, well, actually, it's very uncommon for someone to use more than n variables. Basically unheard of for someone to use more than 12 variables in a mathematical expression or something, right? Like, I think maybe the most sophisticated physics... We've got some physicists in here. Do you ever see like more than like 12 variables in an equation? Yeah, there's probably like 8 is probably a lot. And then I think we're like used to seeing like 6 or something in a more sophisticated thing. But like really, this is like what I saw growing up all the time. It's like, oh, you got 2 variables. Like I can remember 2 things. Okay, right? So someone had to do something. When you're designing the physical computing device, somehow you have to store these variables. And how do you store them, right? Well, you can write them down on a hard drive or on a piece of paper or on a cassette tape. And then it is very slow to write them and very slow to read them. So what did they actually end up doing? You take 32 or 64 transistors, you put them right next to each other, and you put them right next to the bit adder and the XOR and the NAND and all of those sort of circuitry we used in like the SHA lab where we made the bit masks, or in the IX assignment where you made adders and subtract. So all of that stuff exists on your computer, and then right next to it you have 32 transistors, and you just store an I32 in them. That's all. That's a register. But you get a finite number of these, right? When writing a programming language, the only thing that limits how many variables I have is how many symbols I have, or actually running out of physical memory under the hood anyways, right? When I'm using data registers specifically, I get a fixed number of data registers that are made when the wafer is made in a semiconductor fabrication, fab foundry, whatever they're called. Someone sketches into a chip 32 by 32 transistors, and I can only use that many bits. I can only use that many bits at a time. If I try to use more bits than that, it's just not possible. I don't have a way to describe them, right? So a register is kind of the hardware idea of a variable, but it's very important that it is finite. This is the big difference. And this finite thing is coming up a lot because I can put x equals 5 in a register, and I cannot put a string in a register because I don't know how big the string is. If the string is Pride and Prejudice, it doesn't fit in my registers, and I'm not allowed to put it there. So, what happens? We usually think of the stack as starting at some relatively high numeric value. I picked 3,000 because that was the example given. And then the stack decreases. It's like a stalactite that clings tight to the ceiling. It's not like a stalagmite. No one likes caves? Okay, all right. The stalagmites might grow to meet them someday, right? And then they grow together. Anyone like caves? No caving? Okay, all right, that's fine. This is a good cave region. There's like cheese caves and ice caves around here. Okay, so the stack starts high, and what do? You write a value at location 3,000. And then the stack pointer, SP, which remembers my address, it decreases. So it goes down to 299A. And it goes down to 299A because I was secretly using hexadecimal the whole time I tricked you, right? So 299A is 4 less than 3,000. And then I can write the next 32-bit value. And then I go down to 2998, and then I write the next 32-bit value, and so on. The first item is stored at the highest initial address, and then it builds down. Rust's copy allows fixed-size data stored on the stack. So values like I32 are copied when assigned and passed. So what does that mean? Surely I have the diagram on the next slide. Yes, okay, here it is. So I was going to draw this, and I didn't. Good job, me. Okay, so we imagine our stack starting at 3,000. The stack pointer, that's wrong. It starts at 3,000. Okay, so I have my stack pointer. It starts at 3,000, and I say let x equals 5. How is that interpreted computationally? Well, I write 5 to the current top of the stack. I decrement the stack pointer, and nothing is written there, but this keeps track of the stack pointer, so the blank space is the stack pointer. Okay? There's nothing written there. And then I say let y equals x. Y and x are small, they're little, they're finite, they're not big, they're not hard to manage. So instead of just, stealing x or something, I just make another 5. I just make another 5 and I push it on the stack, right? So I have something at 3,000 and something at 299C. Oh, I said A earlier, it's C. I can't actually do hex arithmetic, don't judge me. Okay. Obviously, 0 minus 4 is C. We all understand that, right? Okay. And then my stack pointer increments again. So this is the stack. This is how the stack operates in program memory. Okay. And this is a stack push. I think I need to fix this, but I'm honestly not even sure what I meant, because all of these are wrong. Maybe that's true. No, that's actually completely correct. Okay, hold on. No, I'm going to explain this. The stack pointer starts at 3004. Why? Because before I write something, I increase the stack pointer and then I write it there. So I start at 3004, I subtract 4 off of it, and I write at 3000. Okay, so I'm looking at location 3000, there's nothing there. I try to write a 5. The stack pointer decreases by 4. It moves by 4. Increase, decrease, I don't know. It doesn't really make sense or matter to me. It changes by 4 to 3000, and then I write. It changes by 4 to 299C, and then I write. And then it stays at 299C, right? Because it would change to 2998, but it doesn't yet. Okay. And this describes the push operation. Okay, whew, that was touch and go there for a while. Also, my throat hurts so bad right now, but I was just going to keep going. How many minutes of class do we have left? Oh, that's a lot of minutes. Are we, not even halfway done? Oh, dear. Okay, we'll be fine. Does one of you want to teach the rest of this? No? Okay, all right. Yeah, it could be fun. Yeah, all right. Teaching, it's great. It's life's greatest pleasure, maybe? Okay, all right. Don't say I didn't ask, all right? Okay, so the push operation. The push operation is implementing the stack abstract data type in physical hardware. So what do? Step 1, you decrement the stack pointer. The stack pointer is 32 or 64 bits that just live in a dedicated place in your computer. They're not used for anything else. And we update the stack pointer. We say stack pointer equals stack pointer minus 1. What does that 1 represent? It represents your word size. So we decrease it by 1 word, right? That might be 4, that might be 8. The stack pointer then holds the current top of the stack. It is updated by the finite size of the pushed value. I think, and I'm not 100% sure on this, that the last time I was looking at low-level systems code, You can, in fact, have different word sizes on there, so you can put on a 32 value and then a 62 and then a 16. It looks like you can basically only do 32 or 64, though. But you can do as many 64s as you want, right? As long as you know how many of them they're going to be. Okay, so step one, when I push, I update my stack pointer. And then what do? I look in memory, sort of just the idea of memory, right? The idea of memory is like it can live on a hard drive, right? But it doesn't have to. And I look at memory, and I ask for the stack pointer memory location. So if it's 3,000, I start at the beginning of memory. I go 3,000 bytes into memory. And right there, what do? I store the value of the data register that I am trying to store onto the stack. So let x equals 5. I take that 5 exists in some data register, and I write it to a certain location in computer memory, and then I can look back at it later. The value in some data register is written to the memory location in the SP, to those, sorry. Okay, that is a push operation. The pop operation is the negation of that. How does it work? Given a data register, and we needed a data register both times. When we were pushing the value of the data register. When we're popping, we're taking a value off the stack and we're putting it in a data register. And how many data registers do I have? A finite number, right? So I have my data register. I look up the memory location that's currently in the stack pointer. I go to the memory, I read that value, and I place it in my data register. And then I increment the stack pointer so that it's no longer pointing at that value. Now, something very interesting is going on here that is probably worth thinking about. I am not erasing that value off the stack. I am not erasing that value off of program memory. It's just no longer meaningful. There's just bits and bytes that are on my computer that used to mean something, and I no longer consider them valid. This notion of invalidity is the exact same we see when we try to print an invalid pointer. All of the information in that pointer is probably still there. But Rust has not been making sure it's still there. It hasn't been maintained by the stack property, so we can no longer look at it because something squirrely could have happened. Cosmic rays could have flipped bits. Another process could have come in and written something offensive there that we don't want to see in class. Who knows what happened to those bits and bytes, right? But they're no longer protected. They're no longer safe. So even though they're not overwritten or deleted, they're no longer protected. They're no longer managed. So we don't delete them. We just don't think about them anymore. So a new value is in my data register. A new value is at the top of the stack. The stack is at a different location. That's the pop operation. This is not super easy to show. So I invented this own code snippet. I didn't find this in a textbook or anything. I just know this is how it works. So when I say I know this is how it works, I mean I'm pretty sure this is how it works. So we don't really encode pop in Rust, but here's a pretty easy example. This is not the worst thing you've ever seen in your life. We can create an intermediate namespace. And I'm going to prove to you that this is Rust code, because if it's not, I'm in big trouble. I'm pretty sure I tested this. Okay. Let x equals 5. Let y equals x. And I think I said x equals 7. Is that what I do? No, I say z equals 7. Okay. I'm pretty sure Rust is going to yell at me for not using any of these variables. So I'll be fine. I forgot to say let. Tell you what, you write Python for one semester and you can't write code anymore. Okay, it ran. Okay, it ran. And what does it look like? Okay. So what's going on here? Wrong tab. Okay. X is pushed onto the stack. It no longer lives in a data register. The stack pointer increases and it's now pointing at X. Y is pushed onto the stack. It's the same value as X. There's 2 copies. Okay? But Y is only valid until this closing bracket here. So, as soon as Y is pushed onto the stack, I execute the next line of code, which is outside of a different namespace. So I'm going to do some cleanup. I'm going to pop Y off the stack, and I'm going to silently drop it. I'm not going to look at the value of Y. I'm just getting it off of the stack. So I have a 5. I have a 5 below it. And then that 5 stays there, but I just move the stack pointer back up to the previous 5. Then I'm going to create a Z. So I have Z 7 in a data register. I increment the stack pointer and write the 7 there. So I have 5, then 5, 5, then just a 5, then 5, 7, and the 7 overwrites the 5. The 5 is never deleted. It just is no longer valid. I tried to model that this way. So I start actually here, because otherwise this was too small. So I have my stack. It has a 5 on it, and only a 5. I let y equals x, so I push another 5 onto the stack. So, I think I inverted the numbers here. I don't know. So we push a 5 on. Then we get to the closing bracket, which is a y pop. And then we're now pointing here. There is still a 5 here, but we can't see it. Or maybe there's not a 5 there. We don't know what's there. Something sketchy's there. That's probably where, like, Nessie lives or something, right? Or maybe, do you all say Sasquatch or Bigfoot in this part of the country? Are we? No? Nothing? Okay. You don't have a preference? Yeah, but you live here now. I live in Portland. That's in the city. We don't have woodland creatures. I saw a deer the other day. It's like, hey deer, what's up? I think we talked about the city council race or something. Okay, so blah blah blah. There's something here, probably a mysterious woodland creature, like a jackalope, perhaps. Okay, yeah, all right. So you got your jackalope just chilling, and then along comes who? Along comes Z, and Z lands on top of the jackalope, instantly causing it to become fictional, and then the jackalope is no longer real. This is what your stack looks like. Is this interesting at all? I don't know, but it's important. Okay. Okay, don't listen to that while streaming. Okay. But I spent a long time writing about stack pop, and then I was thinking about Poppy, right? No? Okay. All right. What music do you listen to? Someone say one artist you've listened to in the last 24 hours. Okay, never mind. Daft Punk. Are you excited for the new Tron movie?
Yeah.
Okay.
I'm waiting for an HD player.
Okay, yeah. Okay. Rust ownership. Okay. You may have noticed that everything on the stack is not impacted by ownership. It's not impacted by clones, and it's not impacted by references. The alternative is something called heap allocated data. Heap allocated data, Rust book says this. I don't agree with this. They say, which are too large for simple stack copying? I think that's fake. I think it's that they're arbitrary size. I don't think it matters how big they are. I think if you knew it was exactly 1 billion bits in size, you'd just write it. It can't be that hard, right? Problem is you don't know how big it is, so then you don't really want to store it in an array. Right, the stack functions very similarly to an array that has constant time lookup, and we're doing these pushes and pops. You start pushing and popping things of arbitrary size, you can't do that anymore. So you throw it in a different data structure, which is probably, for me, a binary search tree, and for you, a hash table, right? So these memory types use move semantics to ensure memory safety, where ownership is transferred to prevent multiple variables from trying to free the same memory. So what is the problem that could happen here? Hi. Okay. So if this happens, I set y equals to x, and then y becomes invalid at the end of this. If there weren't ownership, right, you wouldn't know whether you could get rid of this memory at the end of this namespace. The only reason you would know that, due to ownership. Because otherwise y and x would be referring to the same bits in memory. You wouldn't have any idea who's in charge of them. You don't know who owns them, right? So when y falls out of the namespace, you can't get rid of the memory. When x falls out of the namespace, you can't get rid of the memory either, because y might still be around, right? So you can never get rid of any memory. So the memory usage builds up over time. Your performance gradually slows. Eventually the program crashes, right? So this doesn't work, or this does work in Rust, because Rust works. This is fundamentally a different paradigm. So let's think about ownership. We imagine an operation as follows. The value of s is not the string data structure itself. This is capital S string, referring to the data structure. Really, we just think of that as a description, or the address, or the location, or the name, or the key and a key value pair, or something like that. So S is the key and the key value pair of the string data structure. When I set T equals to S, nothing moves. There's no movement. The only thing that changes is the compiler is thinking about the code in a different way. So it's going to interpret successive lines of code differently. But nothing is changing within the computer. The value, the address, the key and the key value pair that refers to the string data structure may now only be referred to as T. The name S is no longer valid. It is no longer in the hash table, right? Attempting to refer to S will trigger a compiler error because the compiler has to stop you from referring to S. Why? So that as soon as you can no longer refer to T, it doesn't have to worry about the memory anymore. So it's protecting itself from having to maintain access to memory that is perhaps no longer intended. This makes sense, trust me. Does this make sense? Can I get some can I get a thumbs check in? You're actually following this? Yeah, it has to be something with Rust. This would have been complete 0% understanding last semester. So, sorry, no, it's not Rust. You're all smart and hardworking. You're harder working than everyone else. That's the difference. Good job. Do you want to give yourself a hand? Do you want a stretch break while we play monkey type? I'm going to go get some water because my throat hurts. Think about what great students you are and how proud I am of you. Okay? I'll be right back. I don't know where my water is, so I might have to find it. You can look at this if you want. That looks pretty good. I made these myself yesterday, by the way. I used to use someone else's until this year. Okay, so this code, of course, works. There's nothing remarkable about this code as code. The only thing that is remarkable about it is how we can talk about it in the context of the borrow system. How do I print S? There's a couple ways. This is one of them, right? Not allowed. Why is that not allowed? Okay. Let's cat this. Okay, so I create the string S. It is the string from Poppy, P-O-P-P-Y, right? And then I let T equals S, and then I try and print S against the law, right? Why is that against the law? Of course, it should be against the law, right? But we don't ever use T. That's fine. We don't care. We never use it, right? It's just there for the sake of example, right? A move occurs. Why? String cannot fit on the stack. There is no way to put something of arbitrary size on the stack. So when we set T equals to S, we can't just make a copy of P-O-P-P-Y and throw it on the stack. That's not allowed. That's unsafe. It's unstable. So instead, T takes ownership of S, which means now the compiler has an easy job. It only has to hold on to P-O-P-P-Y until T is used. S was already used. So this means that when I try and use S down here, the compiler says, hey, no, what are you doing? We agreed you weren't going to use S anymore. We agreed you weren't going to use S ever again. I wrote down a note to myself that if I see another S, I'm going to stop compiling. And what is happening in program memory? We take the S. The S goes away with let T equals S. There is no more S. There is only T. It can only be referred to as T. If you refer to it as something other than T, you break the law. But both S and T are pointing to the same data structure, which stores the string POPPY. So this raises an obvious question, which is that if Poppy doesn't live on the stack, where does she live? And the answer is Los Angeles. I looked it up. I didn't know where she lived. She lives in Los Angeles. She's originally from somewhere else, but I think like all pop stars, she lives in Los Angeles. Someday, when my TikTok really takes off, I'm going to have to move to Los Angeles, and I'll miss you all dearly, but that's the only place that social media influencers are allowed to live, because they have to shop for groceries at Erewhon, which only exists in Los Angeles, right? Okay, so that was really tough on me. But anyways, so Poppy lives on the heap. What is the heap, you ask? That's right. I haven't told you about the heap yet. The heap is the mysterious third thing that is neither the stack nor the registers. It is named after another abstract data type, but it is not even remotely a heap. Actually, I'm a little bit surprised it's called the heap. It is definitely a hash table. Like, it is one of the most hash tables I have ever seen in my life. It is probably a nested hash table, so it's like triple or quadruple hashing or something like that. But it is not a heap, okay? It just means not on the stack. So this is the heap. It's a morass of memory. I had to look up what morass was. It is an area of muddy or boggy ground, or it is a complicated or confused situation. That's where Poppy lives. I think that's actually true. So that's fun. Okay. Here's another way to think of it. You know how next semester a bunch of people are going to sign up for an operating systems class? It's their problem, right? It's not your problem. Now, it might be your problem next semester, and I hope it is. Please take my operating systems class. But you don't have to worry about that right now. This is just a systems programming class. We're only learning how the operating system works. We're not learning how to be an operating system, right? So this hasn't become our problem yet. We're just going to say, operating system, can you hold on to this for me? And it will say, yes. That's all. It seems quite chaotic out there. There's a lot of research into how operating systems store things. There's a lot of security implications. It's a very interesting area, but it is an interesting area in a different way than this class is interesting. So I adapted some slides from Lenovo's description of heap memory. I've been using the term arbitrary size and fixed size or finite size a lot. More commonly is used static versus dynamic. So dynamic is we figure out the size while the program is running. Static is we know the size before the program runs. So we use the heap for dynamic memory allocation. This is the only way to use vectors. This is the only way to make lists. The Python list is arbitrary size, right? The Python data frame is arbitrary size. So the stack is fixed size, last in, first out, managed by the language. Works for small, short-lived data. Usually that means integers. The heap is used for anything of any size when you don't know what order you're going to use it in. So I say any access pattern is random access. So y'all have heard of random access memory, the heap, right? Yeah, it's also a great Daft Punk album. Did I make that up? They have
random access memory.
Okay, was it their last album?
Oh, yeah.
Yeah. Okay. It is manually managed. So the hardware manages the stack for you. Someone, you or the language or the operating system or something, has to manage the heap. Okay. We can think of variables in programs as keys and key value storage, like a hash table or map or dictionary. Do you all say hash table or map or dictionary? Which one do you say from CS 152? What is the standard term at this university?
Hash table.
You do say hash table? Thank goodness. Okay. Everyone was saying hash map there for a few years, and I was like, I don't know what that is. Turns out it was a hash table. Okay. So you got a hash table, right? We can think of numerical memory addresses. So just a number, the memory location. We can think of those as keys, right? It is not super helpful to think of them as indices in an array because this memory has random access. So it's not actually in order. Those numbers are just the name of something, right? But you can imagine that the OS has a hash table of vectors. That can either be the Rust vector or that can be any other vector, but it can be a Python list. It is just basically bit strings of any length. And somehow it stores what the length is too, right? So you can store any data structure in some combination of vectors. I don't think that's too strong of a claim. Okay, common uses. Generally speaking, when we are using the heap, we are looking at, I'll say data structure here, but like a graph data structure, right? So sparse matrix stored as a series of edges and nodes. Dense matrix stored as a two-dimensional array that is an adjacency matrix. Any other form of array, so tensors, multidimensional arrays, parameters for a machine learning algorithm, things like that. And then just vanilla arrays, like here is a .wav file. It is an array of sound frequencies at every 24,000th of a second for 30 minutes, right? And then file-like objects. So here is my video file, here is my executable file, here's whatever. It is mandatory, within reason, to use the heap when size is unknown or may change during execution. Here are 4 examples of things that change size. Files obviously change size. You can read and write from them. We know this. Linked lists can obviously change size. That's why we use them. Vectors are usually just implemented on top of either a linked list or an array list, which also changes size, and then strings. I have to say the word memory leak to you in this class because this is a systems programming class. Memory leaks are a huge problem. They've probably cost like $1 trillion or something. They're really, really difficult to avoid. I have never taught a student that I saw write 0 memory leaks in a class ever. I suspect there's a lot of memory leaks in my code. And the reason I say that is because when I started teaching, I wrote a bunch of ways to check to see if code contained memory leaks, and then I used it on all my code, and turned out all my code was atrocious. Now I write code without memory leaks in it, but that's because I've been grading myself for 10 years, right? It's just a little bit too easy to ask the operating system for memory once, or more commonly, ask the operating system for memory 17 times throughout the course of a program and then only give it back 16 times. It's just a little bit too easy to do that. So, a memory leak occurs when a program asks the operating system for memory and then doesn't give it back. I know what you're thinking. What do you mean doesn't give it back? That's impossible in Rust. Rust can't contain memory leaks because things go out of the namespace, right? So the memory remains reserved, but the memory is used. Okay, we can't do that in Rust. When we use it in Rust, it's deallocated, right? So somehow you're working in a different programming language, and you're able to keep the memory around after you're done using it. Okay, so memory remains reserved, reducing available memory. Not possible in Rust. Huge Rust W. I've been told that people refer to things that suck as Ohio, and so I'm referring to C++ as Ohio. I hope that makes me seem current and up to date. Also, I have family in Ohio, and well, they're probably not watching this. They kind of suck too, so like that makes sense to me. I'm sure they're nice people. Okay, anyone want to say anything positive about Ohio? Yeah.
Have you ever quote gone down in Ohio?
No.
Okay, just
yeah. Thank you for your question. Yeah. Cedar Point is in Ohio. Okay, so there's one good thing about it. Great roller coaster. I think they shut down the roller coaster for being too fun while being in Ohio, if I remember correctly. So, I have got down in Ohio. Actually, I have to issue a correction. It was when I was young and dumb. Okay, so whenever we introduce the heap, I have to remind you all what a heap is. You all know what a heap is, like nod vaguely. Okay, so constant time access to the minimum element, and log n insertion and deletion. Not really great for doing anything other than maintaining a minimum or maximum, right? Does it have anything in common at all with the language or operating system heap? Absolutely not. And it will definitely not come up again in this class unless I give it to you as an assignment to implement on Friday, which I'm not going to do. I'm actually going to do it next Friday, so you're safe. Also, by the way, I don't know how much this bothers you. I have to look at these slides. There's no way that's how you spell language, right? It's UA, right? Why did I type that? I know how to spell language. I don't even, like, the keys aren't even that close to each other on the keyboard. Like, if I just type language a bunch of times. Okay, no, I can't type. That's what's going on. See, all of those are wrong. Yeah, okay, I see what happened. Never mind. Okay, I was going to claim my innocence, but I definitely can't type. Okay, more monkey type for me. Going to go on a strict diet of monkey type. Okay, so, I bet you could, sorry, this is unrelated. So my partner convinced me to start working out for some reason, so I'm like trying to learn how to do a front squat, which never do, by the way. It's absolutely miserable. But like at the gym, right, you're supposed to like take rests between doing heavy compound lifts. I should take my laptop and do monkey type in the rests because so I can keep training. Right, this makes perfect sense. Okay. I think this is what I'm going to do when I'm an influencer and move to Los Angeles. Okay, so, right. So what is actually the heap? Well, sort of like the stack, it's actually just something that exists in hardware. There's just a bunch of circuits put together. And the circuits are called the MMU, which stands for Memory Management Unit. It's a computer hardware unit. What's that mean? It means it actually physically exists, right? It's not a piece of software. No one wrote code for it. Now, in fact, modern MMUs are written in code and then they're printed on silicon, but that doesn't really matter. And what does it do? It basically implements a hash table. The MMU, it is its client is the CPU. So when the CPU is directed by the operating system or a program to store some memory, the CPU doesn't do any of those things. The central processing unit, the computer, right? It says, hey, MMU, I need you to remember that this memory is this big and has this address. And the MMU says, okay. And then does it put that memory at that address? No, it does something completely insane, right? And we don't know. We don't look under the hood. It does something crazy, right? But every time you ask for that number, it gives you that memory back, right? And we don't look inside it, and we don't want to know how it works, right? And the reason we don't want to look inside it and don't know how it works is because the first computers stored their memory on tapes. Later computers stored their memory on rotating media, hard disk drives. And modern computers, like this one, store their memory in solid-state drives. And the same operating system works on all three of those memories. Because when you change the physical memory type, you change the physical MMU, and then all the code just works. So there's something going on in there. And is it like really a data structure? No, it's an abstraction. And is it a leaky abstraction? Yes, because not all of the memory accesses occur at the same speed on every operating system. So we're not commonly going to think about this. There will be security implications next term that are relevant. And in fact, the reason ECDSA is more popular than RSA is because it works better with MMUs. So anytime you need big memory, you have to go through the MMU, and then you're not allowed to think about how it's working because it has to work no matter how the memory is implemented. So I think of this as a hardware data structure, or perhaps an abstract data type even, right? The MMU converts a virtual address. There's a virtual address. That's an address that doesn't correspond to a physical location. That is the address used by the operating system. Operating systems aren't, they're not necessarily concerned with physicality, right? They're concerned with dispatching different programs and maintaining access to things like, maintaining access to the physical resources like the keyboard or the monitor, right? But they do not actually know how the underlying circuitry works, and they shouldn't have to know that. So they just think of things in terms of numerical addresses that refer to memory. The MMU converts this virtual address into a physical address, which refers to electrons, refers to subatomic particles. They actually exist. They can be measured using charge. Okay? Numbers aren't real, but transistors are. And yes, I know that some numbers are real. I'm sorry. I can't say they're fake, right? Like there's just, they don't exist physically, right? This is a big deal in computer architecture. So the MMU, big deal. How do you think about this? The MMU manages circuitry. The OS manages numerical addresses. The programmer and the language in tandem manage symbolic, so X, variable names. And at each point, you have to think a little bit about the thing below you. If the symbolic variable name refers to a string, it lives somewhere different than if it refers to a value. The OS doesn't care, it refers to both of them by a number, but if the number is too large, it has to ask the MMU for help, and if it's small, it's stored in a data register on the CPU. So you never actually know where any of this stuff is, and you don't have to think about it. Those terms and some of the following terms would be on a written in-class assessment if we used those. So we are thinking about going through engineering accreditation for our CS program. I don't know what you all think about that. It should, in theory, be good for you and result in you getting paid more. That's why we're doing it. What that means is in the next 2 or 3 years, someone who actually understands all the stuff I'm teaching you today might come to this university and ask you questions about it, right? On the following slides are the things that I think they are going to ask you questions about, okay? So I'm not going to assess you on this because I haven't really figured out how to write a midterm that has these 3 questions on it and nothing else. And no one has convinced me you actually have to know this stuff for any reason other than program accreditation. But I'm telling you, I would like you to think about this a little bit. Depending on where you get a job or interview or internship or whatever, they might ask you about specifically the TLB at your interview. I remember being asked about the TLB. I don't remember why. I don't remember the context of the questions. But I had to explain what a TLB was to someone once. What's a TLB? Well, it's on the page after this one. Okay. So, paging. An operating system maintains something called a page table. Why do we call it a table? Again, it's a data structure. I don't know what data structure it is, right? Okay, there's tables. There's pages, like whatever, right? And what are those? Well, generally speaking, when you're working with memory at operating system level, they work with 4 kilobytes at a time, because anything smaller than that is child's play and should be handled by the language, right? So I divide up my address space into 4 kilobyte chunks. The physical memory is probably divided into the same chunks, but they're called frames. This is a convention, this is not a requirement. So a page is maintained by the operating system, and it has information in it. A frame is maintained by the MMU and corresponds to a page. The translation look-aside buffer, the TLB, is like, I think it's like this super common vocabulary question, right? It is implemented, I say here in the MMU, maybe in the CPU, right? And what is in there? Well, when I translate my virtual address to a physical address, that incurs some computation cost. Somehow that calculation has to be performed, right? And so if I keep looking up the same page, and I'm the operating system, then the operating system is going to keep dispatching through the CPU to the MMU, request to look at the same frame. But it's going to request that frame by a virtual address, and the MMU is going to have to look at the information on that frame by its physical address. So it has a little scratch pad where it writes down like the 4 most recent physical addresses that it's translated, and it can look those things up faster. And when your computer works, that's why. So some of you may have noticed sometimes when you turn on a program, it is slow to turn on, and then it has high performance once it is running. That is while you are populating the translation look-aside buffer and doing other things, right? But getting memory configured and arranged for high performance usually is something that is slow when switching to a new task and then speeds up over time. And then it slows down again as you incur memory leaks. So my claim is that this is fast as heck. And heck is not a scientific measurement. This is how I would describe the TLB. Oh yeah, it's the part of hardware that makes numerical addresses to hardware addresses fast. I love TLBs. They allow me to, I don't know, do whatever it is. They let you open tabs in Firefox or something. I don't know. The page table is OS managed. The page table is how to look up pages, which are virtual, which correspond to frames, which are physical. Not all of that stuff can fit in one buffer necessarily. Why is that? So this buffer actually has the same problem that all of our variables have, where it's like, well, we can't assume a finite number of memory reads and writes. So if we have too many, we write down all of them in the page table. The operating system manages the page table, and it can relay the page table back to the MMU. So if I'm the operating system and I try to turn on Firefox for the first time in the day, I dispatch to the MMU a request to find Firefox. The MMU doesn't know where Firefox is. It asks me, I, the operating system, am maintaining a page table that says where Firefox lives in physical memory, encoded somehow. I relay that information back to the MMU. The MMU can then go look up Firefox and load it in, but I only have to do that once because the second time I try and open Firefox, which is usually opening a second tab in the main window, I, the operating system, tell the CPU to look that up, and the MMU says, oh, I know exactly where Firefox is, here's another one. So that is ownership, the stack, and the heap. Don't want to do this next time? Let's see. Do we have 12 minutes left? Okay. I'll just do 12 minutes of this and we'll see how far we get. Okay. I'm going to formally teach you struct. I made the decision this term, and I'm curious your thoughts on this, so give me feedback in whichever manner you like. I was going to distribute a survey on if you had any thoughts on my teaching this term, but I did that last year to 60 people and 4 people filled it out. And so then you can't use the survey results because you don't know if it's weird people that filled it out, right? So anyways, I didn't ask you for any feedback. It's not because I don't care. It's because I don't trust you, which is maybe worse. But anyways, give me feedback however you like. I tried something different this term, which I think is interesting, which is I just randomly introduced struct a few times before teaching it formally. I thought that was cool. I felt like when I've been teaching struct previously, it was hard because I sort of taught all of the theory and syntax of struct, and then people were like, why do you do this? Well, now you know. It's in case you have to implement an F16, right? So I'm just going to follow through with the example struct from Rust book. Why did I use the example struct? Am I really going to come up with a clever struct, right? No, that's ridiculous, right? So we're going to write a program that calculates the area of a rectangle. We're going to start by using single variables, and then we're going to refactor until we're using structs instead. So this is the program. Let's go ahead and use this. Where's my circ main? Whoa, that's not what I thought I copied. Okay. There we go. First try. Okay. So what do we have here? We have a width, we have a height. We are going to calculate and then print the area. That doesn't seem too bad. This is how we're going to calculate the area. This is not how I typically write my Rust, right? I have a strong preference to use return statements, but you're under no obligation to do so. So we cargo run this. Oh, wow, really running out of voice. Okay. 30 times 50 is in fact 1,500. Good job. We did it. We did a multiplication. Incredible. Multiplication is super easy unless it has to be infinite precision, right? Then it's impossible. Okay, so what are we going to do here? Well, this works, and it's bad. And it's bad in a very specific way. The area function, if we think about it conceptually, the area function is supposed to calculate the area of one rectangle. And we're providing it with 2 arguments. And that's kind of weird, right? So this has to come with some form of documentation or something like that. But realistically, there could be features other than width and height that we want to maintain with our rectangle. Some of you are CS151 people. And so you remember that the Grechts in that class, they had a width, a height, and they also had an X and Y location. They had whether they were filled or not. They had a color or not. Right? So there could be many attributes of a rectangle that we want to keep together. And so in order to sort of work with these rectangles, we really shouldn't just be passing their width and height around. So I'm going to call this an anti-pattern. Anti-pattern is a solution to a class of problem which may be commonly used but is likely to be ineffective or counterproductive. So some common examples are the God object, which is where you put all code in one class. Man, I'm leaving off a ton of punctuation at the end of lines today. Or a magic number, use constants. Let me show you an example of an anti-pattern. So in this file, this is the example main.rs provided to you for the ED 25519 assignment, which I believe you're all working on right now, probably. I simply keep all of the variables loose within the main namespace. That probably shouldn't happen because I rigorously defined the previous day that this is sort of, I described this in terms of key value pairs, right? So this probably should be a structure or perhaps a hash table or something of that nature. There should be some structure imposed upon all of these variables. And probably when you looked at this code, it could have been the case that you thought, wow, that looks atrocious. And it does. It is an anti-pattern, right? So don't do that. Don't be like me. I was responding to a specific series of design constraints when I made that decision, which is that I didn't want to pass the struct around the day before I gave the struct lecture, right? So that's fair enough. But the struct is the design pattern that negates this anti-pattern. It is generally most like the module pattern in practice. When I write structs in non-object-oriented languages, I tend to end up writing something a lot like a module without actually calling it a module. So I think it is very similar to the module pattern. And you are probably familiar with modules from Python. They are the things that you import, right? It would be more readable and more manageable to group width and height together. So how are we going to do that? Well, and this was a fun interplay today. So I was teaching CS 151 today, and today was the day that they learned about the tuple. So that was very sweet. So I get to teach the tuple in 2 different classes today. So one solution to this is what I refer to as the humble tuple, because the tuple is unassuming. It is not a narcissist, right? It is always there for you when you need to group an x and y value together, and we love tuples for this reason, right? So I can create a rectangle, and I can say the rectangle equals the tuple 30, 50, and then I can say no problem. The area is going to receive something called dimensions, which is going to be a tuple of U32s, and it is going to return the area. This code will of course work, but let's take it and run it. So I'm sorry, I can't help myself. I'm going to write a return statement here. And then I think like dimension is like very long to write, so I'm going to change that to dim. But nothing too particularly exciting is going on here. It's just this is a way that if we're taking the area of one thing, we should provide one argument. And we can do so. And we get the same answer, of course. Is this still great? No. Because what do those 30 and 50 represent? There's sort of no documentation here. This code would be hard to debug if there's a problem. For example, this calculates the area of a rectangle, but it's just called area. The triangle area would be that divided by 2, right? Or maybe, right, depending on what the 30 and 50 represent, right? It could be much more complicated than that. So this still isn't particularly great, but it is a little bit better. We've added a bit of structure to the program, but we've also sort of obscured some things that were clear prior. We previously had something called width and height, and those were meaningful names, right? And so what do we have instead? Well, these are both magic numbers. And that's an anti-pattern. It was on the previous slide. I don't know who put it there. Probably the person that made the rest of these slides. And so what we need to do is we need to shift from the humble tuple to what I refer to as the immortal struct, because the struct has persisted through many languages and will likely persist until the end of time. Structs add meaning by labeling the data. The back pointer to CS151 is the record type. Structs are similar to records in some ways. So we are going to exchange our tuple for a struct. We are going to provide a structure name for the whole, and we're also going to provide field names for the parts. I call the things inside a structure fields. I think they are more commonly referred to as attributes. So let's go ahead and do that. Here we have it. Good bit of code on this slide. Let's go ahead and throw it into NVim. circmain. So, what's the first thing I do? I use the struct keyword. The struct keyword is a lot like the fn keyword, but is a little bit different in that structs do not take arguments, right? So it is just the name of something. By convention, they're capitalized. You know they're capitalized because the compiler yelled at you about F16 and IX. They're capitalized to denote to the programmer that these things are going to be heap allocated. They do not live on the stack. This one could live on the stack. It's fixed size, but by convention, because it's a struct, it won't be. So similar to a function, but we use the struct keyword, and then we use a code block versus a function. The only thing in this code block is variable declarations, and specifically, we give the name of the variable and its type. We do not give its value. Here's how we use it. We create a new rectangle, and this is similar to a function call, but we essentially do a function call with keyword arguments where we specify the name of the internal variable, we colon delineate it, and then we provide the numerical value. So we provide the numerical value the same place we previously provided the type. Easy. How do we use it? Well, given some rectangle, we can look up the rectangle.width or the rectangle.height, and we can perform those same calculations. Now, if I were doing this, I would probably abbreviate quite a bit here. I would probably get down to rect. I would probably just do W and H. And this can be a little more manageable then because you're typing left. We'll just call it R. We'll call this R. We'll call that rect. What else am I doing? This was a rect. Ooh, I don't know what happens if I DE there. Okay. So I think this code will run amicably. Please work. Rect.h not found. Oh, these are R. Okay. And then I just return that. There we go. And so this is the solution to the anti-pattern. Thank you so much. I think is class over now, or do we have 10 minutes? Okay, cool. I'll see you on whatever the next day is, and I'm going to make you implement a linked list. Yay, linked list! Woo! Yay! What even are the other slides? Oh, it's just me complaining about Rust. Okay, that's fine. I shouldn't teach that. That was